So welcome everyone to the very last session of the day. So thank you for taking a seat. Well, everything is running on code, right? And that's why we better analyze that code to some degree, right? So there are obviously various techniques. And today we're going to have two excellent speakers in this space. So I'm very happy to introduce Yannis here from DDARP. So he's a professor also in Athens, currently on leave to focus on DDARP. And yeah, he will be looking into high-value transactions. I suppose these are called attacks also sometimes. So thank you. The floor is yours.
Yeah. OK, now it is. So I'm Yannis from the University of Athens and DDARP, a company we founded some 3 years ago with Neville Grech, who is also an author of this work. So what I'm going to present today is joint work with my co-founder Neville, but also a whole bunch of people at DDARP, mostly former or current students at the University of Athens or University of Malta, of myself and Neville. And we're going to talk about program analysis for high-value smart contract vulnerabilities. And clearly, I expect that everyone here knows what smart contracts are. I'm going to assume we do. So decentralized programs that run autonomously on the blockchain. But my first advertising slide is that this is a perfect domain for program analysis and verification. This is a dream come true for anyone who does work in this space, because correctness is crucial. It means money. All the code is public. There aren't many domains where we have that as program analysis researchers. All executions are public. There are 0 other domains where we have that. And everything is of fairly manageable size, and it's distilled down to its essential complexity because you want to minimize the attack surface. So it's great to be doing research on smart contract analysis. Now, in particular, my research and the DDARP technology of the past years has focused on a specific kind of program analysis, static analysis. So we try to create models of all possible program executions without actually running the program, which would mean follow just one execution. And since 2018, we have applied this to smart contracts, and we've had multiple research results that document this progress, and a few of them will be shown here today. Now, the particular flavor of static analysis that we work with specifies all analysis algorithms declaratively as logical rules. They are in a language called Datalog. It looks like Prolog, only it's massively parallel. It actually, anything that follows, anything that could be true, is produced in parallel. But basically, when we write an algorithm to model a program, we write things like this. And I don't expect you to follow it fully, but you get the idea. To define the concept of loop bound by, we say the loop is bound by that variable. If we have certain relations that already hold, we have an induction variable for the loop called I. Variable is not an induction variable. We have some flow relations. Obviously, all of these are also things that we will define, and we will define them recursively using similar rules. Everything we do can be thought of as mathematical logic, first-order logic with recursion, or equivalently as Datalog. It's a pretty well-founded model. Now, this presentation is very much about a paradox, or an apparent paradox. There's so much value in dollar terms in smart contracts. There's so much program analysis research. And yet, by some measures, there's very little impact. And this is documented both in studies. There's a study in 2021 by Perez and Lifshitz that says that of all published analysis tools, even though they produce true warnings, the actual monetary value behind these warnings is extremely low. And also by the informal opinion of security experts. So you will see top security experts in the space, and they will say very reasonable things, such as, if you have an analysis tool, it can't find the bugs that matter. I mean, at most, they will just catch some details. Or if you're an experienced smart contract author, you will never have automated tooling help you too much. And these are all very defensible positions. Yet, I think there are some counterexamples, and we've had some counterexamples in our experience in the past couple of years. So we've actually had many high-profile white hat hacks, many disclosures of vulnerabilities through our tooling, several of them. And in fact, you may have seen some of these articles or some of these bounty announcements or some of these vulnerability reports. In total, there are many tens of security vulnerabilities that we've found. 10 bug bounties over deployed code. We've gotten 3 million in bug bounties alone by several organizations, and thank you very much. So how do we reconcile that? Tooling is worthless, and yet it can get you multi-million-dollar bug bounties and hundreds or tens or even hundreds of actual actionable security reports. So that's what I'm going to try to give you an idea of. This is going to be a very approachable presentation. I'm going to try to give you insights without much math or anything. So hopefully you can follow everything. So first of all, let's see what questions the analysis can answer. We have a static analysis. What do we use it for? What does it answer? The first thing, so you can have a model in your mind of how we use the analysis to find vulnerabilities, the best example is taint analysis. Taint means what's controllable by an untrusted caller. We say that a value is tainted when it's controllable by a possible attacker. So that's something that we can ask the analysis about. Is this value tainted? Can an attacker control that value? And taint patterns are dominant in practice, so most analysis questions will hinge on tainting. And we can start from very, very simple examples. For instance, if you've seen smart contract code on Ethereum or EVM-compatible networks, you probably know the transfer from function in ERC20 tokens. That's obviously a sensitive function. So clear application of tainting. Can an attacker control owner? Where does owner come from? But not just owner, also spender, also amount. Are these values tainted? That's a very simple analysis question. If we have a really good analysis, it can give us reliable answers. And then, is this code even reachable for an untrusted caller, or do I need to go through authentication to reach that point? So this is where the analysis helps, to give us good answers to this question. Even if you think back to the prototypical vulnerability, you think back to reentrancy. Reentrancy may seem fairly unconnected to tainting at first, but here's a typical reentrancy pattern. We check credit, we make an external call, we subtract from the credit of a certain investor. This has directly to do with tainting as well. There are very natural tainting questions. Is this investor untrusted? Also, could this investor be a contract, or has it been checked before to not be a contract? And at the very end, is this function even callable by an untrusted caller? Or will it fail with a check like this one here that requires the message sender to be someone trusted? So everything reduces down to tainting. That's where we use the static analysis to find actionable vulnerabilities. Now, this gives you an idea of the question. Now, let's get to the point of what is a good static analysis. So we got the question. What are good answers? The principle of static analysis is the following. Static analysis is a game of balancing three independent dimensions, three independent factors: precision, completeness, and performance. Now, yeah, I just gave you a list. This doesn't mean anything. Let's try to see why I make such a big point about contrasting elements such as precision and completeness. The philosophy behind everything you're going to see is summarized by this. Static analysis of our kind, especially, is poetry, not prose. Now, what does that mean, really? It means it can have a fairly fuzzy idea of what the program will really do. And we will see this in multiple examples, and then we will see how we exploit this in designing a fairly high precision, fairly high completeness static analysis. So first of all, standard example of static analysis, let's look at this piece of code. And I know I'm taxing your brain pretty late in the day, but if you try to follow this, we have a value y gets 3, and depending on x and what x will do, I will add 1 to y, and possibly I will also multiply it with itself. Now, if you try to follow this code, if you try to follow it deeply, and you try to follow the modulo, all these conditions here, you will see that the possible values for y at the end are 3, 9, and 16, whereas at first read, if you do it quickly and you ignore all of these, you may think that the possible values also include 4. Turns out not to be the case. I cannot satisfy the first path without satisfying the second. So if I'm not divisible by 2, I'm not divisible by 4. So the possible values in reality are 3, 9, and 16. Take my word for it. You don't need to follow it fully. Now, if I had an analysis that tells you that the answer is 3, 9, and 16 versus another one that tells you the answer is 3, 9, 4, and 16, which one is better? 3, 2, 1. We don't know is the answer because it's never just one dimension. It's never the dimension of precision, which is what's being measured here. It's also the dimension of completeness and of scalability. And I bet you when you try to read this example, at first read, you ignored these conditions. You ignored the x modulo 2 is not equal to 0, and the x modulo 4 is not equal to 0. And that's exactly what a good static analysis may do. A good static analysis may prefer to actually approximate the program execution and tell you that the program can produce all 4 of these values, and this is actually fairly good. You know, you get imprecision of 25%. You give me 4 values back when it's really in reality 3. This could be a pretty good static analysis if this approximation buys me a lot of completeness or a lot of scalability. That's the main game of static analysis that I wanted to emphasize. So if you want to see it as an analogy, as a good nerd, I asked ChatGPT, give me an example of prose versus poetry, and it told me prose is the old man sat on the bench in the park, he watched as children played on the swings and slides, he smiled as he remembered his own childhood, whereas poetry is old man, children play, memories smile. Very poetic. Memories smile. That's exactly what we're trying to do with static analysis. Get a good enough approximation of the program that will capture the essence of the program, approximately, and it will be effective without following everything very precisely. So now that we are armed with this intuitive understanding, let's try to go into a bit more technical detail. Our first big weapon, there are going to be 2, that we've used to find high-value vulnerabilities is what we call symbolic value flow, or SymValIC for short, static analysis. The main paper was from UPSLA the end of year in 21. And what is this? It's a pretty precise analysis. It's path-sensitive. It tries to follow conditions. It mixes values and symbolic expressions. If you don't understand what that is, we'll see examples. It uses a data log fixed point together with a theorem prover, so it has both symbolic reasoning and massively parallel propagation of values, and gets scalability together with some precision through a mechanism that we're about to discuss that we'll call dependencies. And how is it used to find vulnerabilities? Through taint analysis, like we said before. So that's our main client. So what's the real idea here? The dirty secret of program verification for security is that everything has severe shortcomings. Execution-based approaches, by which I mean real execution testing, symbolic execution, as well as model checking, which has abstraction but is very concrete in how it follows the program control flow, these are approaches that are precise but very incomplete. Because they suffer from state explosion, the state explosion problem, and we'll see an example. Static analysis approaches can be complete, but are imprecise. So let's get to an example. You don't need to really follow all this code in detail. We're looking at a function withdraw token. We have state variables. We have a storage variable admin. We have local variables like token, amount, send to that are parameters to the function. And then we have adjusted. The big thing here beyond like having a guard, only admin that checks for some properties, et cetera, the big thing here is that adjusted is a function of amount. When we analyze this program through anything that follows control flow faithfully, be it testing, be it symbolic execution, be it model checking, what we're doing is that we have a state, and it connects all these values. So it knows that adjusted may be 1030 because amount is 1000. And with all these other dependencies, the token has a certain address, send to has a certain value, admin has a certain value. So in other words, execution-based approaches are extremely sequential. They link all these values together. They chain them together. And the way we actually specify this analysis mathematically, you may have seen some of those specifications, but we have a program counter, we have the state of the stack, state of the heap, the storage, in the case of smart contracts. We keep all the state. We keep a lot of heavy stuff with us while we analyze the program. But what we said before is that the philosophy behind this work is that static analysis is not prose, it's poetry. So it can take many, many liberties. And in particular, the standard liberty of conventional static analysis is to treat the values for variables as sets. So this means that what I'm computing here is that there's a set of values for amount. Independently, there's a set of values for adjusted. They do get derived from these values, but I no longer remember that 1030 came from 1000. I no longer remember that 1030 came from 1000 with token being this value. I've lost all these connections. All of these are clouds of values, unordered sets of values. That's the conventional static analysis. That's the poetry that we are allowed with static analysis. So what does this let us do? It lets us solve the state explosion problem and get scalability at the expense of completely destroying precision. So one novelty of our analysis, of the symbolic analysis, is that we pick a subset of the variables. In this case, we pick the variable amount here, and we say this is a key variable. So what does that mean? It means that every other local value I compute, I will link it to a specific value of amount. So I will remember that 1030 is now coming directly from 1000. 515 comes directly for 500. I don't remember the same about token or about send to or about admin. I have anointed amount as a special variable that I will base dependencies on. That's the attempt to get scalability at the same time as precision. So to put this all together, we have a symbolic analysis, symbolic and value flow. So it may compute things such as X can have the value false, can have the value true, can have the symbolic expression. 0 is less than owner value, which is a symbolic variable, et cetera, et cetera. But in reality, what we really have inside the analysis is something that's 3 orders of magnitude larger as a set of inferences, but it looks like this. X will have the value false, or 0, when Y has the value 0, Z has the value 1, and caller has the value owner, et cetera, et cetera. And in fact, we have 2 kinds of dependencies that simulate whatever you would think of as stack and heap. We call them local and global dependencies. So we do all this symbolic reasoning through a massively parallel data log engine together with a symbolic solver, a theorem prover, effectively. And there's limited top-down reasoning. There's limited solving of equations and a lot of bottom-up reasoning. Tell me all the true theorems up to depth 5. And all of those, I will use them for simplification, et cetera. So our architecture looks like that. We have something massively parallel that talks to a symbolic reasoning and mostly sometimes gives requests for solving equations, but mostly gets back massive results of whatever is true based on all the data that we've fed in. So this kind of analysis is our first major weapon. What's our second major weapon? Well, we just discussed how to get good answers. I never told you how to know how to ask good questions. And that's just as important, if not more important. So to take a very simple example, I may want to ask the analysis, is the first argument of a swap call tainted? Well, where did I come up with that? How do I know that swap is a sensitive call? How do I know that the first argument of the swap has any kind of monetary significance? One answer is we have humans specify. We have human experts specify that. The problem with this is it's not too scalable because there are lots of DeFi protocols that come online every week, and they have new sensitive operations, and we cannot really rely on security expertise to provide more and more of those. So we'd like to do something a little better. And the answer is what we call corpus analysis, which is learning from what deployed contracts already do. So for any contract that gets deployed, we have a whole bunch of local analysis that give us a lot of data that are then used by any other contract, such as, well, what functions have monetary significance? What functions make their arguments flow to transfer or transfer from? What functions perform initialization? What functions do a delegate call? What functions allow reentrancy? Or what functions perform permission checks? Or make a call without performing a permission check or after performing a permission check? And a whole bunch of these properties. These are all summarization properties. So in effect, corpus analysis summarizes the behavior of all deployed contracts in two ways. What does the contract do? And we use this so that the callers of a function can be analyzed better, have a model for what we're calling. And what is the usual behavior of callers? For instance, do callers have the second argument of this call untainted or tainted? And we do this to detect deviations. And to come up with good examples here, first of all, we have to realize that all of this is done recursively. So we analyze function bodies, we analyze calls to functions, but where are those calls to functions? Inside the function bodies. So this feeds back. And we can have lots of examples, such as how do we detect reentrant operations? Well, bar may be a function that's known to call functions on its second argument. By itself, it's not reentrant, but it can be reentrant when I call bar with a tainted second argument, and now foo, the caller of bar, is reentrant. These are the kinds of things that we can get from our corpus analysis recursively, from our local summaries that get propagated to callers. But in effect, if you want to have a single example to stick with you, that's going to be the example. If I see a swap and I see 2,000 callers that have the first argument of a swap be untainted, so before you reach that, you check the value of that, or you check the value of the caller, and then I see one caller that allows that first argument of the swap to be tainted, well, that's pretty suspicious. I'm going to issue a warning there because I found a rare exception to the calling patterns for that particular function. And that works very well with our own public tooling because we do have an explorer, a security-oriented explorer, so we do analyze all deployed contracts by default anyway. So I give you a good idea of the techniques that we're using, of our technology. Now I'd like to wrap up with a couple of observations really quickly. I have a little over a minute and a half. Some insights on static analysis in industry versus academic research. I've done static analysis in academic research for 15 years and program analysis in general for over 20. Now, I will not get into that for lack of time, but you all know in academia, it's bad when stupid solutions work well. We want complex solutions. In industry, it's fantastic when stupid solutions work well. Let me get to something very specific here. Here's a question I ask in all my talks, and people are surprised to hear the answer from experience. Think of whatever you would consider a good program analysis, whatever is your definition of good. What do you expect this good analysis to do? Out of 100 contracts, and fractions are OK for an answer, how many would you expect to be flagged? And out of 100 flagged contracts, how many warnings do you expect to be truly valid true positives. Think about this for 5 seconds, because I may surprise you in 2 or 3 slides. But the questions should be clear. So first of all, for the first question, how many contracts we expect to be flagged, you have to realize the range varies tremendously. So here's a list of some analysis that I ran over 200 some contracts. And you can see that some warnings fire for 5% of the contracts, others for 0%, others for 0.5%, others for 24%. So the range can be huge. If you were to just see this, which analysis would you think would be the most useful is the first question. And then for the second one, for both questions, I think we have surprising answers. I think that in academia, we have the wrong metrics for anything that counts. Because warning rates at 0.5% seem useless. Try to publish a paper where your warning rate is 0.5%. You know what the program committee will say? Well, 199 out of 200 contracts are correct already. So the whole impact of your research is to improve by 1 out of 200 contracts? That's completely bad research as far as program committees are concerned. In practice, if you are to find high-value vulnerabilities, your warning rate will probably be under 0.5%. High-value vulnerabilities are rare. So that's the first answer that's kind of surprising. These are the warning rates that will find you high-value vulnerabilities. Those are the most valuable analysis. And very quickly, to my second controversial position here is that in academic research, in static analysis, the community where I come from, we expect very high precision. We expect analyses that have very high, over 60% precision. Otherwise, the results are not publishable, because we're used to synthetic benchmarks or very shallow bugs. For deep, high-value vulnerabilities, even 5% precision is awesome. It means I get 20 warnings to inspect. 1 out of 20 times, I make a lot of money. So my answers that people find surprising are like this. Out of 100 contracts, how many would I expect to be flagged? If it's more than 0.5%, I'm trying to improve the analysis further. Out of 100 flagged contracts, how many of the warnings do I expect to be valid? I'm happy if it's 5. Of course, I would like it to be 100, but I'm happy if it's 5. And that's it. Thank you very much.
Very good. Dan, you have a question?
So we're getting lots of reports that large language models are good at finding these types of vulnerabilities.
I'm sorry, could you say again?
We're getting reports that large language models are very good at finding these types of vulnerabilities. I notice you're not using them at all. So I'm wondering if that's...
We are not, and actually those are not the reports that I've seen. The reports I've seen say that LLMs have been pretty bad at finding these vulnerabilities. But maybe, we've been very surprised by LLMs. We definitely want to integrate them in our tool suite, in our research, in everything. And I wouldn't be surprised if in the future they are very effective. But not right now. Right now, we're not using LLMs. Our statistical techniques are much weaker than that on the corpus analysis.
I see. Yeah, thanks.
I was curious about this one of these steps that you had shown in static analysis about solving equations. So what does that look like? Is it modeling each of the participating variables in the code? And are you feeding it to a solver, a constraint solver, or an equation solver that will output some? What does it look like?
Yes, and that's most of the equations. They come from what are called path conditions, and you can think of them in terms of the code examples. You can think of them as equations like this. Like, I want to solve this equation here. I want to solve this is true. Oh, I'm sorry. Well, I need my slides, please. Thank you. So most of the equations that we're solving symbolically with a solver, they are in response to path conditions like this. So I may want to produce the value true and false for this if condition. So I want to invent values for amount for that. So most of our equations so far are based on, they're linear together with some bit manipulation. It's not a very rich theory that we're solving, but it's perfectly sufficient for the domain. And we are trying to innovate on the speed and the reads based on domain-specific insights.
Thank you so much, Yannis, for this wonderful talk. So our last speaker of the day is Alessandro. So he's a research scientist at Aleo and Kestrel. So he's doing formal verification. And in particular, we'll discuss today formal verification of zero-knowledge proof circuits. So,
Okay, go ahead. Yeah.
Great.
Okay. Hello. Okay. So there are three important elements in the title of the talk, and I'm going to describe all of them in turn, starting with a little background on zero-knowledge circuits, which are used in zero-knowledge proofs, for which I will use the color green throughout the presentation. So a zero-knowledge proof is something that somebody called the prover can use to support the claim that they know a secret X that satisfies some property P. And when faced with a zero-knowledge proof, somebody called a verifier will be compelled to believe that that's the case, but they will not learn anything about X itself, and that's the zero-knowledge aspect of this protocol. On the other hand, the predicate P, the property, has to be known to both prover and verifier, because they must know what they are talking about, what the proof is about. And that's where the zero-knowledge circuit comes into play, because if we look inside a proof, we'll find a circuit. There's also other information that doesn't concern us here, but the role of the circuit is that's how P is represented in the proof. So it defines the predicate P. This is what it looks like inside. It's a set of constraints. Each constraint is an equation, an equality between two arithmetic expressions that involve variables, constants, operations, all interpreted in a prime field. So essentially, it's the integers modulo a prime, a large prime for security. And these constraints, these constraints must have specific forms that depend on the zero-knowledge proof method used. For example, R1CS is a popular form for this. So this is how P is represented by this constraint. So first, the input parameter X of P corresponds to one or more variables in the constraints, depending essentially on the data type of X. And then the constraints are a bit like a program to compute P of X from X, in the sense that the solutions to the constraints correspond to the values of X that satisfy P. Okay, so this works well, it's very expressive, but it's a very low-level definition, right? If you look at this, for example, the second constraint is an XOR. The third constraint is an if then else. And if you haven't seen that before, that may look surprising, but that's what they are. So here, that takes us to the core problem that we're trying to approach here, which is here we have the zero-knowledge circuit, low-level definition of P in the zero-knowledge proof, which a prover and the verifier use to run this protocol. But most likely they have in mind a higher level view of what P is, what they're trying to prove about this secret X. I'm going to use color red for high-level definition, specifications, etc. So this high-level definition could look, for example, like a program written in a high-level programming language. This is an example from our own Leo programming language developed at Aleo. The details are not important, but you can see that there are pretty conventional constructs, data types, operations, control flow instructions, things like that. It does something, and that's what program verifiers think about. Okay, we are running a proof for this. But then the zero-knowledge proof has these low-level constraints. And so the problem is, how do we know that these are the same, that it's the same P? Because if they are not, then the zero-knowledge proof may not quite prove prove what is expected to be proved. So that's where the second element of the title comes into play, which is formal verification, which is how we address, we tackle this problem. In particular, we use the ACL2 theorem prover, but the approach works with other theorem provers as well. So let's see how we do that in a little more detail. So first of all, note that the circuit can be for all of P or for some subcomputation of it. So we still have the same notion. So we can just drop the requirement that it's the whole thing. We just have a circuit for some computation and a high-level definition for it. The high-level definition is like a specification. Let's use more proper formal verification terminology here. So let's replace that with a specification. So we have a circuit and its specification. So we do this, we formally characterize the circuit, mathematically. We formally characterize the specification, and we formally prove their equivalence. Formal proof is different from a zero-knowledge proof. They are at different levels. There's no prover and verifier. There's just a circuit and a specification and a theorem about it. So that's what the formal proof is. It's about a zero-knowledge proof, but it's not a zero-knowledge proof. So let's look at an example to develop a little bit of intuition that then we will generalize to more general concepts. So here's a simple circuit, which is a division circuit. That's its specification. It says that we take x and y, we divide x by y. If y is different from 0, put the result into z. Otherwise, it's an error to the distinguished value e for error. So let's look at the first constraint. So if y is different from 0, we can divide both sides by y, and so we get that w is the inverse of y. If we substitute that into the second constraint, we get that z, sure enough, is the quotient of x and y. This is division in the prime field, so it's always well defined if y is different from 0. Also, importantly, if y is 0, the constraints have no solution, because the first constraint becomes 0 equals 1, impossible. That matches the fact that it's an error in the specification. Okay, so let's try to generalize a little bit these ideas. So formally, we can say that a circuit is a mathematical relation. Let's call it R over the variables. Why is it a relation? Because for some values, it is true. All the constraints are satisfied. For other values, it's not. So it's a relation over the variables x, y, z, and w. X and y are input variables, dividend and divisor. Z is an output variable, is the quotient. What about w? That's an important concept in circuit. It's an internal variable, an auxiliary variable. It's not part of the computation. It's something that the constraints need in order to express the computation. It's an internal thing. Okay, we'll come back to this. It's very important. So the characterization is based on the specification, not on the circuit. The circuit just has variables. They're all equal, all the same. But when you relate that to a specification, then they take on these roles of inputs, outputs, and auxiliary. Let's look at the specification. What is it in general? We can say it's a functional computation, let's call it F, from inputs to outputs or error. So let's put it here in the box. So in this case we have f of x of y equals either the quotient or an error. Okay. So now we have R and F. But how can we relate them formally? One is a function, one is a relation. You cannot quite relate them directly. But we can define a relation from F over the input and output variables like this. Let's call it S for specification. So we can define that S holds on inputs and outputs if and only if the output is the result of applying the computation F on the inputs and it's not an error. Okay, getting closer. Now we have two relations, but they don't have the same shape. The second one has 4 arguments. There's a W. But then, so the auxiliary variables, their purpose is to supply some value for which the constraints are satisfied. So we can derive a new relation, let's call it Q, from R, which is obtained by existentially quantifying over the auxiliary variables. So we can say Q holds on X, Y, and Z if and only if there exists some W such that R holds. Now we are in business. We have Q and S, they have the same shape, and that's what it means for the circuit to be correct, that these two are equal. So that's circuit correctness. So these generalizes to arbitrary circuits and specifications which have input variables iota bar, output variables omega bar, auxiliary variables alpha bar, and any computation f that returns something under some condition or error under some other condition. Let's look in a little more detail at the correctness. Yeah, so it's a bidirectional implication, so it means it has two directions. The correctness is if and only if. So the only if direction means that every solution to the constraints corresponds to a non-erroneous computation. We call this soundness of the circuit. The other direction, the if direction, says that every non-erroneous computation corresponds to a solution of the constraints. We call that completeness. This is different from their meaning in zero-knowledge proofs. Again, there's no prover or verifier. There's a circuit and its specification. That's what these refer to. To prove soundness, we expand Q into R, and with a sleight of hand, we turn the existential over the antecedent into a universal over the whole implication. We don't need to deal with existentials. For completeness, we can also expand Q, but we cannot play the same game. We need to deal with the existential, typically by exhibiting logical witnesses for the auxiliary variables alpha. So this is the general framework for formal framework for circuit correctness. Another important notion that concerns circuits is that they have an implicit hierarchical structure. So that means that there's circuits, sub-circuits, sub-sub-circuits, and so on. But it's implicit, that's why I'm using dashed lines. It's not really there. I'll explain more shortly, but for now, assume it's actually there. Assume the dashed lines are real. Here's an example. Our division circuit from before, we can view it as consisting of two sub-circuits, one that inverts y into w and one that multiplies x and w into z. It's a very simple example, it's trivial, but it applies to more complex examples, as you can imagine. So that's where the third important element from the title comes into play, because we can use this hierarchy to do compositional formal verification. By this, it means that we verify circuits bottom up, and in particular, to verify a circuit, we can replace its sub-circuits with their specifications. So, for example, let's take circuit 3, we verify the equivalent to specification 3, and now we can, to verify circuit 2, we can forget about circuit 3 and use specification 3. Why? Because it's simpler. It's a way to manage the complexity, to keep each verification simpler, because specifications are high level, constraints are low level, so it's easier to deal with specifications. So that's how it works. We do it for specification 2, and we do it circuit 2 to specification 5 to 5, 6 to 6, and so on and so forth. I could have made this shorter, I know. Let's go back to the hierarchical structure of the circuits. So where does it come from? Or not, since it's not really there. Well, it sort of comes from the way circuits are constructed, which is via libraries, typically, such as our own SnarVM or the Bellman library, very popular, or other similar libraries. So I'm going to use the color yellow for these libraries that build circuits. So conceptually, these libraries, they look like this. They have code to generate circuits and to do other things. For example, there could be some code to generate the division circuit, and this code will call code to generate the sub-circuits. So we see the hierarchy in the yellow box, right? And there could be multiple instances of the division circuit in a large circuit, right? So the circuit may look like this, but the lines are dashed. They're not there because the way the libraries work, they just accumulate these constraints in a flat list, and there's no boundaries, So this is really what they look like. There's this ocean of constraints. The variables don't even have good names because typically they are generated using increasing indices. So if you look at the constraint, you say, okay, there's some stuff I can't even find where the division is. Okay, so then how can we do compositional verification if the structure is not there? Well, we do it like this. It's hard to reconstruct, like I said. We replicate the constructions in the theorem prover. So I'm going to use color blue for the theorem prover. And here is some ACL2 code. It's Lisp syntax, so it's an infix notation. Define introduces a function in the theorem prover. So we define a function called field div circuit to construct a circuit for division. This is parameterized over the specific variables to use, so x, y, z, and w. And as you can see, it calls other functions to construct the sub-circuits. Again, trivial example, but it applies to larger examples. So you can see blue box and yellow box have a similar structure, right? You see the hierarchy in both. How do we, and these are based on a formal model we've built of R1CS in the theorem prover, obviously, for syntax and semantics. How do we know that we are building the same circuit? We can run the blue code, so we can run the yellow code, run the blue code, and compare. It's a syntactic comparison. So every time we use the yellow box, we can run the blue box and make sure we get the same thing. And then our formal proofs, which apply to the ones generated by the blue box, will also apply to the ones generated by the yellow box because they are equal. So let's look in more detail at what the theorem looks like. Okay, so here we have this field div circuit function in the theorem prover, which formalizes our division circuit. In fact, formalizes all possible instances of the circuit for all possible variables. There's also a specification, right, that comes into play. So we write that one in the theorem prover as well. The theorem prover is very good at writing specifications. So we write a function for this called field div spec, which takes the three parameters, x, y, and p. That's the prime of the field, must be explicated. And just as if y is 0, then return an error. Otherwise, do prime field division of x by y, exactly like the red box says. So this formalizes the specification. So now we are ready to prove things about these two functions, the spec and the circuit, because they are both formally defined in the theorem prover. So we prove correctness for all possible instances of the circuit, because these are generic. So here is what the theorem looks like. Let's make a little bit of room. So it involves these two functions, and it says essentially that for every possible choice of the variables, x, y, z, and w, and for all possible assignment, ASG, of values to these variables, the circuit is satisfied by the assignment if and only if the value of the output, in this case z val, is the result of applying the specification function to the values of the input variables. There's also something else which I will discuss later. Just pretend it's not there for now. In any case, this captures formally proves the equivalence of circuits and of the circuit and all instances of the circuit and the specification. So it's the proof itself is compositional. So to prove this theorem, we first prove the correctness of the inversion circuit, then of the multiplication circuit. Again, trivial in this case, but think of a more complicated example. And we use these theorems to prove this theorem. If there is a larger circuit that uses division, it will use the theorem we prove for division and maybe other theorems. So that's where the compositionality of the proofs come into play. It's important to note that the parameterization of the circuits goes beyond the names of the variables. Some circuits have a varying number of variables and constraints. Here's an example. The details are not important, but it's converting a field value x into bits y0, y1, y2, etc. The number of variables and constraints varies. So this is captured by an ACL2 function, which has as parameter a list of variables for the y's, so that also gives the size of the circuit. So when we prove correctness, which we do by induction, obviously, we prove, in fact, for all possible sizes. Also, the prime is generic, so it could be also a prime of 1,000,000 bits, and not that we use it now, but if it were, we've proved it. So it's not limited by the size. So we have used this approach to verify many of the circuits in our SnarVM library, the constructions, where it's ongoing work, and we've obviously increased confidence in the correctness of the constructions, but we also found in the process a couple of bugs and some optimizations. Some optimizations were fairly significant, resulting in saving about an order of magnitude of variables and or constraints. We ran into a solvable scalability issue, which I will describe next, along with the solution. And here's the issue. So it's related to the auxiliary variables of these circuits. The problem is that they are exposed as parameters of the ACL2 functions. So here's again the division circuit, and here's the ACL2 function. Remember, it has inputs, outputs, and auxiliaries as parameters. So if there is a larger circuit that uses division, its ACL2 function has to have a parameter for the W of the division circuit. If there is an even larger circuit, that also has to have a parameter. So you can have many instances of division. Some circuits have lots of internal variables. This gets out of hand at some point as you build a bigger circuit. There's a lot of these intermediate variables. They're internal, so why are they exposed? The exposure also comes up in the correctness theorems because, if we have, here for division, again, let's bring back the theorem. It's time to unveil what was in the dots. The theorem has to talk also about the values of the auxiliaries. Otherwise, it can be an if and only if. It has to talk about that. And this propagates up. So again, it's not a deal breaker. You can still handle, but it gets really, really hard to handle. So there's a solution for this, which is actually this formalism we have developed, which is called unimaginatively PFCS, which stands for Prime Field Constraint System. It's a generalization of R1CS along 2 dimensions. One, equalities can be between any kinds of expressions. They're not restricted to the R1CS or other form, and that allows us to capture other formalisms besides R1CS. Second, more important, is that constraints can be grouped into named predicates, and that captures hierarchy explicitly. To clarify, PFCSs are not a new zero-knowledge proof system. Their purpose is just for specification and verification. So they are just for that. So let's see very briefly how the problem is solved. As we use them and develop them more, there will be future publications. So, but here, let's take our beloved division circuit from before with its implicit hierarchical structure in R1CS form. This is how we represented in PFCS form. So firstly, the inversion circuit will be a predicate called inv with the parameters A and B. The names don't matter; they are local, to the definition. One equality constraint, no auxiliary variables. Multiplication circuit, predicate called mol with parameters U, V, W. Doesn't matter. One constraint, no auxiliary variables. Division circuit is predicate div, which calls the other 2 predicates and has one internal variable, W, obviously, nothing changed, we just repackage things. But here's the really, really important key point. The semantics of the body of a predicate is still the relation R from before, the one that involves auxiliary variables. However, the semantics of the predicate itself is the relation Q, the one over just inputs and outputs. So essentially, this captures the existential quantification over the auxiliaries. So we have formalized PFCSs in the theorem prover, like we did for R1CSs, and we are porting our work to PFCS form, and this solves that scalability issue. Here is a graphical recap of what I've discussed. You can find more information in the paper and also on our website. Thank you.
Well, wonderful recap. Thank you so much. First question.
Yeah, it was very interesting that great talk. It was very interesting that you showed that the the Q function does not have the W internal variable, auxiliary variable, while the right-hand side is having auxiliary variables in the multiplication and the division functions. Now in the division function, the W happens to be an internal output which is fed to the input of the multiplication function. So can we characterize and say that an auxiliary variable can be treated as one that is an output in one function and an input to another function?
Yeah. So when you connect different circuits together, sometimes an output variable of a function becomes an input, and then in the combined circuit, that becomes often an internal variable. Yeah. So the status of whether it's input or internal depends on which circuit we are looking at. Does that answer your question? Did I understand your question correctly? Did I understand your question correctly? Yeah. Absolutely.
Thank you.
Sure. Thank you. Victor. Yeah.
Thank you for the great presentation. How long does it take to create these proofs for, let's say,
it depends.
transfer?
Yeah. Some are very simple, a matter of minutes, literally minutes. Others really have to think about it. Usually my process, I tend to, if it's a little more difficult, I do a pencil and paper proof first. I spell out the argument. Yes, some of them are fairly elaborate. They take some thinking. You see them, you say, yeah, I guess that seems to do the right thing, but that's not enough. You really have to know. And sometimes you have to look at a lot of cases. So yeah, it can take hours sometimes. Between. Then you have to convince the theorem prover of that. Once you have a pencil and paper proof, and you have to be more detailed. Yeah.
Now I had another question.
Yeah,
Which was the theorem prover? ACL? What was that?
ACL2. Yeah, ACL2.
ACL2. So are there other theorem provers similarly in this domain?
Yeah. ACL2 is one of a handful of the main general purpose interactive theorem provers in the world. Others are Isabelle, Koch, Lin, PVS. At some level, they are the same thing. They are very different, though, if you look at the language, the logic. But yeah, they can be all. This could be done with those other provers as well. ACL2 is used a lot in hardware verification. It's used at Intel a lot. It may be the prover that has the most industrial use. Among those, the others, not necessarily the most users, but the most industrial users. Yeah.
Thank you.
Sure. Mike.
Hey. So 2 questions. Does that mean that as long as all the constraints are recorded, they can be proved in any order, basically? Like, can you reorganize the constraints at will, just as long as you record all of them?
Yeah. The order doesn't matter. The semantics is invariant to the order. Yeah, that's.
And then the second one is, what happens when this specification changes slightly? Do you have to re-verify it?
Yeah. We do that all the time. Some of the circuits, when we found optimizations, they change. So it's a process. You kind of look at it. You change, and sometimes the proof goes through without change. Other times it doesn't. Then you have to look. We need to change something. It's still true, but it needs a little different guidance. The theorem prover. Yeah, it varies. Yeah, it can be very simple or very hard, depending on the change.
Well, thank you. That was very helpful.
Awesome. Thank you so much.
Thank you.
Very cool. All right, we're concluding day 2. So thank you all for being here, and maybe see you at your favorite meetup.